Welcome to the multiple reactor system under the edge of polymer reaction engineering. Now, before we go into detail of this concept of multiple reactor system, let us have a look at what we have discussed in the previous lecture. We discussed the basic concept of reactor design in the previous lectures. Now, in this particular lecture, we are going to study with the performance aspect of different type of reactor which are being used in the polymer processing, polymer synthesis. Then we will discuss about the plug flow reactor in series and parallel type of system. We will discuss about the mixed flow reactor in series and parallel. We have a look about the different type of reactors in the series, sometimes the combination of the reactors, etc. And then we will have a discussion about the best arrangement of ideal reactor system. Now, when we talk about the preference for the reactor, so from the observation of different points, we can estimate that what type of reactor should be used for respective reaction system. Now, if we take for all n is greater than 0, that means positive order. So, for some desired conversion and the flow rate, the volume of the mixed flow reactor is always larger than the plug flow reactor. So, we can say the plug flow reactor is best for use. Let us have a look in this pictorial diagram that for all positive order reactors and for the same conversion, the volume of CSTR is greater than the PFR. So, therefore, based on the economics of the reactor, the PFR is termed to be the best one. Now, you see in these plots, if we say the conversion versus 1 upon R A. Now here if you see that for the shaded region, if you see that there are two type of shaded region, one here and second one is here. Now, here the upon FAO and this one is n is greater than 0. Now, here this Vm upon FAO. So, if you see that the performance etc. in this particular reactor system, Vm upon FAO, that is the initial feed rate, is greater than Vp upon FAO, and that is why it is said to be that the PFR is the best one. Now, for sometimes people may ask that what may happen to the negative order reactor system. So, n is less than 0 for the desired conversion and the same flow rate, the volume of the mixed flow reactor is always lesser than the plug flow reactor. So, MFR or mixed flow reactor is termed to be the best for the use of such kind of a system. Let us have a look about this particular thing. So, let us assume that we are dealing with the same conversion and here the n is less than 0. So, volume, if we talk about the volume of the system, then in that case again if we see or if we plot minus 1 upon Ra versus conversion, then if you see that there are two shaded regions. Now, this is represented by this one and this is represented by this one. So, here Vp upon FAO is greater than Vm upon Va naught. Now, Vp is the volume of plug flow reactor and Vm is the volume of mixed flow reactor. So, you can say that at this approach the mixed flow reactor is termed to be the best one. If we talk about the preference for the reactor, now sometimes for zero order reaction it will not depend upon the conversion. So we can use any type of reactor. So for all n is greater than 0, that means the positive order reactor, the irreversible reactions if we take into account, whose whose rate increases with the reactant concentration, then a plug flow reactor. Usually as a concentration drop progressively throughout the reactor length, is more efficient than the mixed flow reactor. So as in the case of mixed flow reactor or MFR, concentration drops immediately to a low volume. Now when we talk about the PFR reactor in series, now if plug flow reactors of different volumes, they are connected in series, the product stream out from the first reactor will become the feed stream for the next reactor connected in series, and so on. Now, if one reactor volume is not sufficient for the required conversion, then such type of series or a parallel connection may be used for having the better conversion or enhanced conversion or desired conversion. Now, let us assume that n plug flow reactors, they are operated in series with a different volume each. So, the fresh feed connected to the first reactor, we will discuss this pictorial diagram. So, the fresh feed, when it is connected to the first reactor having the initial reactant concentration with no conversion. Let us have a look about this one. Now, here you see that these plug flow reactors, they are connected in series. Right. So, here you may say that the conversion is x1, here you can say the conversion is x2, here we say the conversion is x3 up to xn. So, now this is, so there are n plug flow reactor, as you see in the figure, they are connected in series, and the fresh feed we are supplying to the very first reactor, this having the initial reactant concentration without any conversion, that is sometimes referred as FA naught. Now, as the feed passes through the reactor length with the time, the different conversion of the reactant obtained at a different length of reactor. So, at the exit of the first reactor, the product contains remaining concentration of a reactant and converted product. Then it is further entered into the next reactor with some reactant concentration, and so on. So, if we see this particular figure, here we are supplying the fresh feed, and here if you see that, if you carry out the product analysis or the outlet analysis, here you will find that there are some unreacted reactants, and then there are some sort of a product that may become the inlet stream of this second reactor, and subsequently it goes into the different direction. Now, if we take sometimes we need to take the material balance. So, in that case you need to calculate the performance equations. Now, when we carry out the performance equation, the first and foremost thing is that you need to carry out the material balance on this reactor. So, let us say that this is one of the reactor, that is ith reactor. So, if we talk about the material balance on say ith reactor, then it may be represented as Vi upon Fa naught, that is the initial condition, xi1 xi dxa upon minus Ra. Now, for there, if we say that there are n reactors, as we can see over here, there are n reactor in series, then it can be represented as Fa naught. Let us write this, that n reactors are in series. So, you can see this is F naught, V1 plus V2 plus and so on plus Vn upon F naught. Now, this can be represented as Xa minus Ra plus, and this can be Xn minus 1 Xn dxa upon minus Ra. or it can be represented as V upon F A naught is equal to x naught is equal to 0. That is the mole conversion at the start be 0, and then it goes to n dxa upon minus Ra. So this is one of my desired equation for the things. Now, if we see that from this observation, we can conclude that when n different plug flow reactors are operated in series, then the plug flow reactor can be used in place of all having the same volume V as the sum of n different plug flow reactors connected in series. Now, sometimes you may ask a question that if we have utilized this PFR concept in series, then why not in the parallel? Because for the optimization purpose of the performance, you may need to look into all the best options available to you. So, let us have a look about the plug PFR in parallel. So, if the plug flow reactors are operated in parallel, then the fluid system having the same composition in each. In that case, the reactors in parallel may have the same volume upon feed ratio or tau in each parallel line. Now, let us say, let us try to develop the equation for this particular thing, that is the plug flow reactor in parallel. Now, here this is these are the reactors, you can say. You can see this is the basic arrangement of parallel stream. Now, here this is the A, this is the B, and this is the C reactor, and this is the stream 1 and stream 2. Now, if a fluid have same composition, fluids have same composition in both the stream, then the reactors in parallel have same V upon F or tau, which we have represented in each parallel line. So, these are the parallel lines. So, the total volume for reactor for S1 is Vs1 Va plus Vb. Now, we can write for the plug flow reactor that is in parallel. So, we can write that Vf upon F S1 is equal to V upon F S2. Similarly, if we can write like this Fs2 Vs1 upon Vs2. From this relation, we can calculate what amount of feed must be fed to the system, either S1 or S2. So, this is again a very much important thing which we need to look into. Now, let us talk about the mixed flow reactors in series. Now, mixed flow reactors in series, again a very good concept, and let me draw a basic figure for this one first. Now, this is your basic battery of your mixed flow reactor. Here this is the basic concept. There are several reactors in conjunction with the other one. Now, let us have the coordinates of each reactors. This one is Ca naught, Xa naught, Fa naught, nu naught, V1 tau 1, V2 tau 2, and all these reactors are having the, then this is Vi tau I, and this is Vn tau n, and here we are having the Can Xan nu. So our main focus of attention will be to these reactors. Now, if you see that we considered n mixed reactors in different volumes, and you see here we have used the different volumes V1, V2, V3, Vi up to Vn. Now they are connected in series, and the composition of reactant is uniform in each of the reactor due to the homogeneous mixing throughout the reaction mixture in the reactor, but decreases from reactor to reactor. Now if density change in the reactor is 0, that is then for the mixed flow reactor it is more suitable to develop equation in terms of concentration rather than conversion. Now if we are taking the two different size of mixed flow reactor connected in series, then best for will be for where you may observe the positive order, that is n is greater than 0, and for the same conversion a small volume reactor will connect first, and for if we take the order to the negative, that is n is less than 0, then larger on the later on larger reactor will be connected first. So that is for the two dissimilar volume condition. Now if this stepwise decrease in the concentration sometimes suggests that for the larger number of units connected in series approaches plug flow reactor of the volume same to the sum of all n reactor volumes. So if we try to write the balance equations for all kind of a reactor, then balance on the first reactor can be written as first reactor. Then we can write the performance equation of CSTR, that is tau 1 is equal to V1 upon nu 0 is equal to Ca naught x1 minus Ra1 is equal to Ca naught minus Ca1 upon minus Ra1. So if we say that that if we try to rearrange the things, then it may become the Ca naught minus Ca1 upon K Ca1. This is my equation number 1. Now if we take the balance on second reactor, then tau 2 is equal to V2 upon nu Ca1 minus Ca2. So for first order reaction, nu naught on K Ca1, this may be termed as equation number 2. Now if we say that from equation number 1, if we recall that equation number 1, then tau 1 is equal to Ca naught minus Ca1 upon K Ca1. So it can be tau K Ca1 is equal to Ca naught minus Ca1, or tau K Ca1 plus Ca1 is equal to Ca naught, and Ca1 into 1 plus tau K Ca naught, or Ca1 is equal to Ca naught upon 1 plus tau 1 K. Now this becomes the equation number 3. Now if we take the equation 2 into cognizance, then it is tau 2 is equal to Ca1 minus Ca2 upon K Ca2, tau 2 K Ca2 plus Ca2 A1 to Ca2 plus 1 plus tau 2 K is equal to Ca1. Now if we write the equation with respect to the Ca2, then it becomes Ca1 upon 1 plus tau 2 K. Now this becomes the equation number 4. So from equation 3 and equation 4, we can have Ca2 Ca naught plus upon tau 1 k plus 1 tau 2 k plus 1, and that becomes the equation number 5. Now sometimes we may take some special cases. So these special cases that is referred as like case 1. If we talk about the case 1, then there may be tau, if tau 1 is equal to tau 2 is equal to say tau I is equal to tau n, and let us say tau, and V1 is equal to V2, then Ca2 will become the Ca naught upon 1 plus tau k square. Now if we say that n reactors of same volume in series, if n reactor of same volume in series, then Ca naught upon 1 plus tau k n. So this is the more generalized equation. Now let us take the another case, that is case 2. Now if we say that n different volume, if n different volume of CSTR in series, then Can is equal to Ca naught upon n, I is equal to 1 plus tau I k. Now again we take some special case, tau 1 is equal to tau 2, tau I equal to tau n, then it can become Can is equal to Ca naught upon 1 plus tau n k to the power n. Now this is again one of the more generalized equation. Now if we take the case 1 again for equal volume MFR, case 1 for equal volume MFR, then it can become Can is equal to Ca naught upon 1 plus tau k to the power n. Now tau n reactor, this is can be represented as tau I n upon k Ca naught upon Can to the power 1 upon n minus 1. Now if there are various cases, now if say n is n tends to infinity, that is number of reactors are operated in series, then this equation for the mixed flow reactor approaches to the plug flow reactor. So MFR, the equation attributed to MFR approaches to PFR. So in that case tau p is equal to 1 upon k ln Ca naught upon Can. So this equation will become, now this is the performance equation, for PFR having volume same as sum of volumes of all reactors connected in series. So by this way we can generate the performance equation, which are equally applicable for various system. Now if we talk about the n mixed flow reactors, those connected in series, then the required performance equation can be generated for the calculation of conversion and concentration after each and every reactor. Now let us have a look about the different type of reactors in series, because this is one of the most common thing in various industrial approaches. Now, if there are three different size and type of reactors are operated in series, let us have a look about the figure first. Like this, there are three different type of reactor. You see that one is this one is MFR, this one is PFR. So, V1, V2, V3, and here you are feeding with XA naught, FA A naught, CA naught. Then you may experience some conversion over here. Then the output of this reactor is subjected to this reactor having this X2, and here you are having the X3. So, 1, 2 and 3 systems are in series. So, now first you can say that one is the mixed flow with the volume 1, the second is the plug flow reactor with the volume 2, and the last one is again the mixed flow reactor of having the volume 3, V3. So, first one charge with the fresh feed in this particular first reactor, then the reactant or the product stream is the reactant line or inlet of this PFR, then again the outlet of this PFR is the inlet line of this MFR. So, this particular type of approaches are very common in the industry. So, in this type of reactors connection, it is more convenient to calculate the conversion of reactant at a location with respect to the reactor. Now, as point mentioned, which we have already mentioned in this type of thing in the previous segment. Now, the conversion can be defined as the total number of moles of reactant that reacted up to the point per mole of the reactant feed to the first reactor. Now, let us have this the mole balance equation for reactor 1. So, mole balance equation for reactor 1. Now, FA1 FA naught minus FA naught XA1. Now, if we talk about for reactor 2, then it may become FA2 is equal to FA naught minus FA naught XA2. Now, if we talk about the reactor 3 for this reactor, so for reactor 3, FA3 is equal to FA naught minus FA naught A3. So, these are the mole balance equation. Now, where if we say that the what is XA1, that is the total moles of A reacted up to point 1, that means up to here, divided by moles of A fed to first reactor. Similarly, you can write XA2, that is the total moles of A reacted up to point 2, that means up to here, divided by moles of A fed to first reactor. So, similarly, we can write for XA3. Now, for reactor 1, if we talk about the reactor 1, that may be represented as V1 upon FA naught is equal to XA1 minus XA2 upon minus RA1. Similarly, if we try to write the equation similar type of reaction for reactor 2, then it can be represented as V2 upon FA naught is equal to XA1 XA2 dXA upon minus RA2. Now if we try to write the equation for reactor 3, then it may become V3 upon FA naught XA3 minus XA2 upon minus RA3. So sometimes graphical representation usually help in this approach, and you can draw the graph with the conversion. So here this is the conversion. You may have such type of a graph where you may represent the first reactor conversion like this with respect to 1 upon minus RA, that is V1 upon FA naught. Similarly, you may represent another mixed flow reactor, that is V3 upon F naught, and here this may be represented as for FA naught. For your convenience, I am again giving you the battery of that particular reactor system. Now here you are getting X3, and here you are having the CA naught, FA naught. Here V1, that is X1, V2, then this is V3, and here you may have this X2, this is coming out, and there X3. So this is the graphical representation for reactor in series. So this is the best way to look into this the performance of these different type of reactors in series. Now sometimes people may ask that what should be the best arrangement for ideal reactors. So there are several points which we need to describe, and we need to take some important point for the best arrangement of these ideal reactor. For all reaction, if we are having the positive order, that is n is greater than 0, whose rate concentration curve is usually rises monotonically, then the reactor should be arranged in series, because this is a very complex type of system. That is why this type of an advisory is always required for this to handle the situation. Now if n is greater than 1, the rate concentration curve is usually concave. The reactor should be arranged in a manner so that to keep the reactant concentration is as high as possible. Now sometimes you may see that if n is less than 1, then the rate concentration curve is convex. The reactor should be arranged in such a manner so that the reactant concentration should be kept as low as possible. Now if rate concentration curve passes through the maximum or minimum, then the arrangement of the units depends upon the shape of curve, desired conversion and number of units available. Now the examination of the curve between the rate inverse and the concentration is again very important factor for the best arrangement determination that need to be addressed. Now if we take an example of a reactor arrangement, as we discussed in the previous one, that a reactor of a different type in series, the arrangement can be made with respect to the having the things V1 is less than V3 in our mind and n is greater than 1. Then if we are handling such type of sequence, the sequence of the reactor is plug flow reactor and the small mixed flow reactor, and at the last large mixed flow reactor will suffice. So the volume of those things play a very vital role, and if you see that in the previous discussion we have discussed this thing. V1, V2 and V3, all three reactors, they were having the different volumes. So if they are V1 is less than V3 and n is greater than, then you may have a different configuration. You may have because this is quite obvious that which reactor should be having the volume on the higher side, or sometimes people may say that the reactor may have all volumes equal. So this is a very debatable thing. So you must have these things in your mind. Now for determining the arrangement of ideal reactor form, the usually a graph is drawn between 1 upon minus a versus x a. So, the area should be minimum for the best possible arrangement. Now, here you see that we have drawn a graph here 1 upon minus 1 upon R A, and this is the x A. So, you may have this type of curve where sometimes n is greater than 0, here you may have n is less than 0, here you may have n is greater than 0. So, the maxima and minima. So, you are having different zones. So, the PFR. Now, for n is greater than 0, the minimum area required is for PFR. If n is less than 0, that is the second arrangement, the area under curve is minimum for CSTR, and for n is greater than 0 for this third zone, the area under the curve is possible only for the PFR. So, this is for the PFR. So, the arrangement would be PFR plus CSTR plus PFR. So, this would be the arrangement. Now, in this at the last we discussed about the multiple reactor system, and we discussed the various configurations, whether it is a mixed flow reactor or plug flow reactor, and how we can arrange, whether they are in parallel or they are in series, how we can discuss and how we can address the performance equation concept in this arena. And we especially emphasized with the plots, so that the area under curve you can calculate, and then you can decide that which kind of arrangement is best suited for your system. For your convenience, we have enlisted couple of references. You can utilize those references for the further study. Thank you very much.